Select the major product of the following reaction. So in order to determine the reaction pathway, or the reaction product, we need to determine the reaction pathway. So we need to look at what is our starting material and what are we reacting it with. So we see that we are starting with a tertiary alkyl halide. And we know that halides are good leaving groups because they are weak bases. So we're looking at the possibility of a substitution or an elimination reaction. So we have a tertiary alkyl halide. And what we know about tertiary alkyl halides is that if it is to undergo a substitution reaction, that tertiary carbon is too crowded for the concerted mechanism. So this would have to be an SN1 substitution if it went through a substitution pathway. If it were to undergo an elimination pathway, this could be E1 or E2. So by looking at the structure of the halide, we basically ruled out SN2. Okay. And so then we're going to need to look at what we're reacting it with to decide between these remaining three pathways. So we see that we have potassium tert butoxide and that we're heating this reaction up. So your tert butoxide, if we expand the structure out, so potassium is your counterion, which means the oxygen that is next to it has a negative charge, and then we have a tert butyl group. So if we wanted to describe this, we would say that this is a strong base. It is also sterically hindered, or bulky or large. Any of these terms mean the same thing because of the branching that is at that carbon that's directly attached to your anion. So this is a strong, bulky base. Okay, and so as soon as you see a strong base with a tertiary alkyl halide, you're looking at an E2 pathway. So now we know that this is E2. Okay, and so E2 is your concerted elimination. So in an E2, your leaving group and your hydrogen have to be 180 degrees away from each other. So this is what we've got our alpha carbon where our leaving group is. So we'll label that alpha. We have our beta carbon where the hydrogen that we're going to remove is. And so they have to be oriented either so they're 180 degrees apart now, or there should be a way for the molecule to rotate to get them 180 degrees apart. And then your base, so we'll just use a generic B-, would abstract that hydrogen. So we're forming a bond between the base and the hydrogen. From the carbon-hydrogen bond, those electrons collapse in to form the pi bond, and then we break the bond to the leaving group. And so that has to be able to take place all in one step. That also means that it's going to get a little bit crowded. And that's where the bulky base comes in to play. So we want to look at where do we have beta hydrogens, what carbons should we be considering? So here's our alpha carbon, right? And then we have a beta carbon here on the ring. So I'll draw a hydrogen attached to that. And then we also have these two methyl groups, which are also beta carbons. And so these two methyl groups are completely equivalent to each other. We have free rotation about this bond. So I'm going to draw some hydrogens off of this lower methyl group. And the only reason that I am choosing this instead of here is just on this flat paper, it's easier to draw some hydrogens here. Okay, so what's going to happen with the bulky base is it's going to remove a hydrogen from a beta carbon, but it's going to favor the less stable, less substituted alkene. And that's just because of steric hindrance. Okay, so tends to form the less substituted alkene. So if we consider the structure that we're starting with, if we were to remove that green hydrogen, we would form a really stable tetrasubstituted alkene, but that's just not physically going to be possible with that strong bulky base. If we wanted to remove that green hydrogen, we'd need a small base. With this large base, it's going to remove one of the peripheral hydrogens from this methyl group or this one. In either case, the product will be the same. So we'll just draw an arrow coming in to remove one of these hydrogens. I'll at least go for the one that looks 180 degrees away from that leaving group. Although these are all equivalent, we again have free rotation. So we will react with that beta hydrogen. The electrons will come in to form the alkene, and we will kick off the bromine leaving group. So if we take a look at that structure, we have our cyclohexane and we have formed the alkene that is less substituted out here. So once we've drawn the product, we want to look and pick it out of what we have here. And although it doesn't maybe look like it at first glance, this structure is the same as C, because either, let me highlight that a little bit more. These are equivalent because you have free rotation about that single bond. So that if you draw it this way and the answer looks like this, don't be thrown off, they're still the same molecule.